Good day to you all. Welcome back to another video of mine. Today we will be talking about transmission lines, which is a bit apart from my last few videos. So let's get started because this is going to be very long. So a transmission line is essentially a conductive line that transmits a certain signal. Alright, so we have the source and we have some transmission line and then we have the load. The goal, hopefully, is for all the power in the source to end up in the load. Any any power that is not in the load is wasted at the transmission lines. And the transmission line noise or the transmission line attenuation is what we don't want to have. So in electrical engineering, the study of transmission line is often correlated with efficiency since they want to transmit as much power as possible from a generator to the load or the houses or whatever. For electronics engineering, we want the signal to be we want signal integrity. So we want the signal, as much of the signal to the load. Why? Because the the usual signals in here have usually 5-volt peaks or whatever, and this is very low. And because of this low voltage or low power, if some of it gets attenuated, you would not be able to receive a signal at the other end. So it's important that we have to know the properties of a transmission line. So let's get started. This is a transmission line. Let's try building the equivalent circuit using its implied effects on on the current passing through it, right? So current is passing through it, and we do have some sort of input voltage and on the load here. So we expect the wire to have some sort of resistance. Every material in the universe, save for some weird superconductors, have resistance. We will call this R. Now, this is AC, or it's close to AC. We tend to imagine the source as pure AC, but in reality it's a combination of a certain amount of frequencies and whatnot, and that's what makes a signal, according to Fourier theory. But we can imagine this is AC. So in AC, the magnet hold on the electric field that moves back and forth creates a changing electric field, and the changing electric field generates a magnetic field. All right, that magnetic field effect can be simulated using an inductor, which creates a magnetic field in response to a changing electric field. Let me just change. Where is this? There we go. Next, in between a transmission line is some sort of dielectric. Usually this is air. So that's just two wires hold up like that without anything between. Well, not without anything, but it has air in between them. But sometimes this can be Teflon. I've seen that a problem once. Or polyethylene, which is some sort of plastic. And those have some conduction between one of the wires and the other. It's very small. This conductivity is very small, but it does have some. And we can also simulate that using a resistor, because insulators are just big resistors, right? But since this is parallel to the load, we can't use R here. We need to use conductivity G. And forget L for inductance. Now the last one, since this is a conductor, an insulator, or a dielectric, and a conductor. And by the way, the word dielectric comes from two electric conductive surfaces, and that's between them, right? And this insulator is between two conductive surfaces. That's why it's called a dielectric, all right? And if you have a conductive surface, a dielectric, and another conductive surface, what we end up with is a capacitor. which we will now have C as its measure. Alright, so this would be a lot simpler if instead of having 4 parameters, this only had 2 parameters, which we're going to do here. Now, the resistance and the inductance in series and AC, we can add them together, not right now, but we can add them in such a way it will become impedance. All right. So remember, the impedance of a resistor is just the resistance, because the impedance of a resistor is independent of the frequency of the AC voltage. Okay, the impedance of an inductor is J. J is square root of -1, which is usually I, and then omega, which is 2 pi f. This is the radiant frequency, and then L. And then of course, for the impedance of a capacitor, this is now 1 over J omega C. Alright? So, for this one, we have an R and we have an L, but we need the impedances of them, and then just like resistance, we can add impedances in series together. So, the impedance of this is going to be R, the impedance of this is going to be J omega L. And we can replace them together. We can replace them. We have R plus J omega L. This is impedance. We have to label that as impedance. There. Now, this is a bit trickier because it is in parallel, and we know resistance is in parallel, right? We need the 1 over RT equals 1 over R plus 1 over R, and then the indices. And that's going to be a bit difficult, but we can have the reciprocal versions of it. The reciprocal versions of resistance is conductance G, so we can just add conductances together. And that is in DC. In AC, we need to take into account the capacitance, and its equivalent in AC. The equivalent of G in AC is susceptance, admittance, which is in Y, and it's the same behavior as resistance. So let's remove this one because we don't need inductances anymore. We do have the impedance of a capacitance here, but we need the admittance now, so we can add these together because the admittance and the conductance have the same property in parallel here. So the admittance is just the admittance of capacitor is just 1 over the impedance of C of the capacitor, so the reciprocal, right? So this is just J omega C. Move this one. There we go. And the admittance of the resistor here is just the conductance. YG equals G. So again, the resistance or the conductance is not affected by the frequency whatsoever. So now we have the admittance of these two together, and since they're parallel, we can add them together, and we get the total admittance of this second part. Y equals G plus J omega C. Alright. And there we go. Now let's label them together. I'll call this 1, I'll call this 2. So we have Z1 and Y2. Now, R, we have the 4 primary parameters, R, L, G, and C. We have combined R and L, and we have combined G and C in here. These are the primary parameters of this system.